errors in numerical methods. Okay, fine. And there may be a problem. My handwriting is much smaller than Eli's. So some of you may have struggled to see it out, especially if you are watching in mobile. You are done. Okay, so you may have to possibly switch over to laptop or something in a bigger screen. It may be visible. Fine. So now we will come back, resume our discussion, and we will look into those two errors I was telling about. That's the truncation error and the roundoff error, and which is what basically matters in when we deal something with the numerical technique or the computers. So before going into there, so we need to know to identify the error. We need to know how a computer is going to deal the number I'm giving it to it. Okay, I told you the computer cannot multiply or divide anything. All it can do is only addition, and that too not proper. Okay, we will see why I am saying this, why I am telling this repeatedly. So okay, so let us see how in a computer my number is going to be represented. You know, computer is in binary. There's only 2 fingers, unlike my 10 fingers. Okay, so we all know that our decimal system started because we had 10 fingers. We used to count using 10 fingers. That's how decimal system came into picture. And you know about that sexagesimal. What is that? QB. You know about the Babylonian counting. Anyone knows about the Babylonian counting? They count up to 60. You know that?
No, sir.
Oh, you don't know that? That's very interesting.
I heard about it, sir.
Yeah. The Babylonians count like this. See, this is one of the pointing finger. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then they use this for the multiple. Okay, so that makes it 12 into 5, that makes it 60. So that's why they have the 60 base system. That's why your angles all come in the 60 base system. Because Babylonians, they were very strong in geometry and things. So still we stick to that 60 base system. So that's one of the means this the different number systems. So we have decimal. Most of the people stick to this 10. The Babylonians are someone who counted up to 60. So, well, in our case, a computer can count only up to 2. So we have to stick with only two digits. So and what the numbers we deal in our day-to-day life, there are 2 types, right? One is integers, another one is the real numbers. Either you call it a real number or it is a floating point. To a large extent, integer representation is exact. How an integer is represented in a computer? For example, let us have 4 bits. That is a binary digit. Okay. I'm just skipping this fast because I know Nilay has already taught you quite many things about this. So if I have 4 bits and each bit have only 2 options, right? Either 1 or 0, on, off or 1, 0, whatever you call. Okay, so then I have to represent my numbers, integers. My integers goes like 0, 1, 2, 3, 4. If it is positive, another is a similar thing I can have assigned integers also. Am I right? So this is the way it goes on. So now I have to represent this integer in a computer. How the computer does it? Suppose if the computer have 4 bits. Okay, so then what is the maximum combination I can get? 2 to the power of 4. Am I right? So that is how much? 16. Sure. Correct. Fine. So how am I going to start is how the computer stores these integers is it starts with 0, 0, 0, 0. I will represent it at 0. It goes to typical like your vehicle odometer. When this becomes 1, it becomes 1. And then when the next round this becomes 0 and this all becomes 0 here. The next round this becomes 1 and this becomes 0. This make it as 2. And the next round it makes this 3. And the next round this becomes 1 and this becomes 0. Then I get 4. So you keep on doing like that. Okay. This is the way. So an integer can be stored in a binary form. Okay. So now if you have 4 bits, what is the maximum biggest number you can store? Starting from 0?
15.
15, yes, 0 to 15. If it is unsigned, correct? The moment if you want, because it's all without signs, the moment if you want to give a sign, you have to reduce one digit, one bit, you have to allocate for sign, either take it zeros to be a whatever you can for convenience. For typically take 0 as a positive and 1 as negative, I think so. Anyway, fine. Okay, so then you are left over with only 3. Am I right? Correct. So then the maximum number will be what? 8. Correct. So when you, yeah, what I'm saying is when you have these 4 bits, and suppose if you wanted to represent a signed integer using this 4 bit, that means you are going to allocate 1 bit for the sign. Am I right? So this represents whether it is a positive or negative. Maybe positive I will call it as 0 and negative I may call it as 1. Okay. So then the rest of the numbers I have to use it for representing. Clear? Am I making it clear? So what is the smallest number and the largest number I can store in this configuration? Tell me. So 2 to the power of 3 is 8. Am I right?
Yes, sir.
Yeah. So what will be the smallest number?
0.
Come on. I have signed bit.
-7.
Yeah. Minus 8.
No, -7.
Minus 8.
Oh, okay. 8
Correct? Minus 8 to 7 plus 7.
plus 7.
Yeah. Plus 7 is the maximum number I can store and minus 8 is the smallest number I can store. So now if I keep on adding more and more bits, I can keep extending my number ranges. Correct? Am I right? So I can represent my number exactly. There is no problem at all. If my whole mathematics is going to deal with the numbers between minus 8 to plus 7, the computer is going to represent this number exactly. Am I making it clear? So if I have more and more bits, if I have 8 bits for example, let us take 8 bits. If it's 8 bits, what is the maximum number it can, 8 bits, if I allocate 1 for sign, so it becomes 7, right? So find out, tell me what will be your maximum, in the case of 8 bits, what is the minimum and the maximum number? Tell me.
255.
Pardon?
Minus 124, minus 128 and plus 127.
Correct. Minus 128 to plus 127. Is everyone clear why this is coming up?
Yes, sir.
Yeah. So if anyone have a doubt, ask me. Okay. So because 8 bit, 1 bit you are allocating for the sign. So the leftover is a 7 bits. You have to find out all the combinations based on the 7 bit. Always the positive number will go 1 less because you are taking 0 also as a positive. You got it? So in a negative you go minus 1 to minus 128. When it goes to positive, you start from 0. So you have to add up 0 also adding as a positive term. So that's why it stops at 127. Okay? So this is the way. So now you can see, if I keep increasing my bits, I can represent my integer exactly what the way I want. And all my calculations also can be very precise. Then why I am calling this computer as a stupid? Because my life is, in real life, I am not going to have integers. What am I going to deal is with the real numbers. And I need a computer to handle my real numbers, not the integers only. So the moment I speak about the real numbers, computer mess up the numbers. Why it mess up the numbers is, so you should know how the real number is stored in a computer. Nilay already explained you a bit about this. And I am repeating it because Nilay put it on me. He told me that when Sunder teaches this, you will understand it more. So, well, so let me explain you. What do we mean by the how a real number is stored in a computer? So, people in a computation physics, they normally call this a floating point number. Okay. a floating point number is represented to the computer in this scientific form, whatever you call, that is something, what we write is there will be a sign bit into mantissa into the base to the power of this exponent and a bias. So let us come. This is the way any real number is stored in a computer. We will come one by one. Okay, so to look into it, so this base is which is the base unit you are using in term of for a computer it is 2 because the base 2 system. So now we will not look at, to understand this we will use a base 10 system, but that's easier for us to understand. Suppose let us take for example I am going to store a number. What I am going to have? I am going to store the 1052.7. If I want to store this real number, how my computer is going to do is it converts it into 0.10527 into 10 to the power of how much? Tell me. 4. Am I right? Correct. Plus 4. Am I right? I am doing a mistake. Are you people listening me? Can you able to listen?
Yes.
Yeah, perfect. So this is the way. Then what the computer stores is, now you can see in this representation I am having how many sign I need to store? One sign for this mantissa part, another one is for the exponent part. Correct? Am I making it clear? So basically the computer what it stores is this has to store this sign bit and then this part, that is 10527, and then this sign bit and then this exponent form. Correct? So basically you have to store one sign bit, another sign bit and the mantissa and the exponent form. Okay? So instead of storing two sign bits, what the way they do is they add up, they either add or subtract a large number with it. Okay, so what am I going to do? Suppose for example, let us take a case. I am going to deal with a number which goes from 10 to the power of minus 20 to 10 to the power of 20. I am not going to deal with any number beyond this range. What am I going to do? I am going to use the bias, or I'll call it as E, which is 20. And then I add all number with this. Okay, so then what happens? So this becomes 0, correct? Am I right? Are you people able to follow me?
Can you please tell what you are writing on the board because we are not seeing it properly?
Oh, okay. Now it's coming proper?
Yes, sir.
Yeah, now it was stop. See, what happened, I'm saying is, for example, I'm going to deal with a problem which is going to have my numbers ranging from 10 to the power of minus 20 to 10 to the power of 20. Okay, so this is the numbers I am going to deal in my problem. So I know I am not going to use any number beyond it. Okay, in that case what happened, I will add up some number E. Okay, and in this case I will take my E to be, for example, let us take it 20. When I have my E equal to 20, this becomes 0 and this becomes 40. Am I right? Correct.
Yes.
So what is the advantage of that is I have eventually killed my sign bit. Okay, all I have to remember is, okay, I need know this is the bias I am using. So all my calculation I will have the back of the mind I am using a bias of 20. I am using this bias just because I wanted to avoid having a sign bit in my exponent. Okay, so that's what. Suppose for example you are in your yeah, okay, so that's how that's what the whole concept of what this bias is. Can you people understand now clearly what it is? So bias is some large number, either you subtract or add with the exponent. Either if you subtract it becomes negative, am I right? If I put it minus, then becomes minus 40 to minus 0. Whatever it is, everything you can. So basically what the whole idea is, you have to remove the sign bit. So the bias is a large number which is which is added or subtracted with the exponent such that your exponent will become unsigned. In that case, your computer representation looks very decent. This is not going to give any added advantage. Okay, this is only your convenience of representing the numbers. So then what happened? Then I can always store only one signed bit and the mantissa and the exponent. Correct? So the computer stores only these three quantities: S, mantissa, and the exponent added with the bias. Okay. So now these are the three things a computer is storing. So now, for sign you need only one bit. So mantissa you need to allocate some number of bits to represent, because this is a mantissa. You have to allocate some bits to represent this mantissa. Similarly, I kept here 4, so there can be any number. So you have to allocate some bits to represent this part, exponent plus bias. Correct? Now, okay, for example, let us take my exponent. I have, what I will do is, okay, let me have an 8-bit exponent. If it's an 8-bit exponent, okay, so it can store, I'm saying this is exponent, okay. Am I making, are you able to understand what I'm saying? So what is the power I can get? Suppose, for example, let us take it in signed form only. So if it is 8-bit, 1 bit is allocated for sign. Okay, so it makes some minus 128 to plus 127 is the exponent I can store. Am I making it clear?
Yes.
Yeah. So in this case, if I add up a bias of 128, correct? If I choose E equal to 128, my exponent becomes unsigned. Clear? Yeah.
Yes, sir.
Yeah. So this is the whole idea of exponent. Okay. The exponent is basically whole idea of the bias. The bias is basically to add it so that you don't have a sign bit in the exponent. There will be only one sign bit in storing the number. That will be your this sign bit, which is in front of the mantissa. Okay, so this is what a computer stores in a number. And now, so given this, yeah, I think I have some, okay, that I can show it after this. Okay, given this form, now you can tell me. So there are, unlike an integer you allocate just a certain number of bits to store the integer. When it comes to real number, that's not the case. In integer, you need only one sign bit, and the rest of all the bits are allocated for the integer to be stored. But when it comes to a real number or a floating point number, so we have one bit for sign, and then you have to store two quantities for a real number, correct? One is the mantissa, another one is the exponent. Now you tell me, so you have to allocate certain number of bits for storing the mantissa and certain number of bits for storing the exponent. Clear? So now you tell me, what decides the smallest and the largest number that can be handled among these quantities? Tell me.
So,
You got the question?
right?
Pardon?
So can you repeat the question?
Yeah.
Exponent?
Yes. Okay. The question is this. So you are storing a real number, storing a floating point in this representation. So the computer allocates one bit for the sign and certain number of bits for the mantissa and a certain number of bits for the exponent, right? A real number is stored in these three. One sign bit, one mantissa and one exponent. Certain number of bits are allocated. So now I am saying, so I have decided, so let us say sign bit, leave it is only one bit. I have allocated x bits for mantissa and y bits for the exponent. Now, among these x and y, what decides the smallest and the largest number the computer can handle? Pardon, tell me.
Minus 2 raised to x to 2 raised to x minus 1.
Correct, that's the exponent. So my exponent I am allocating y bits, for example. And for mantissa, I am allocating x bits. Okay, now the question is, understand the question clearly. I am asking what is the smallest number and the largest number that can be represented by this configuration in my computer. What decides that? Which is the quantity? X among, because this is only one, you have to leave it. So there is x bit and y bit. Okay, which is the quantity which decides the maximum and the minimum number that can be represented in this configuration? Not clear?
Why?
Perfectly. Why? Why? Right, because exponent, y is the one, because exponent is the one which decides me the smallest and the biggest number. Correct? So what, yeah, question is there? Yeah, so what,
Computer will convert it into its own representation, so that's why y will be the one to decide, right?
exactly, yeah. So y will be the one because y is the one.
Accuracy of decimal.
Pardon?
Mantissa is just for the accuracy of decimal.
Exactly, correct. So your y decides your exponent, so that is the smallest number, and mantissa decides how precise, how accurately you are able to represent the real number. For example, if this is not 1052.7, instead of this, I had a number of say 1052.7865037218995. Okay, if this is my actual number, okay, up to what digits I am going to make it as 0.10527865037218995. Up to what digit, what accuracy I can store this number is decided by the mantissa. You got it? So how a number is accurately represented, that is decided by the mantissa, and what is the smallest and the largest number I can represent, that is decided by the exponent. Am I making it clear now? This is the how a floating point number is stored in a computer. Am I making it clear, everyone?
Yes.
Okay, so good. So then you can still me, okay, I allocate, okay, I will show you some of the typical configuration in a double and a single position. Let me, yeah, you can see here. Yeah, you can see the screen. Can you people see the screen?
Yes, sir.
Yeah, you can see I have written the top single position and the bottom double position. Okay, you can count and see how many bits are allocated. This is the way typically a real number is stored in a computer. Okay, the first bit, the 31st bit, which starts from 0 to 31st, so there are 32 bits. That's for single position. The 31st bit is for the sign. You can see that, and the next 8 bits is used for the exponent. Okay. When I mention here exponent, it means exponent minus bias. Exponent added or subtracted with the bias, so that I don't need a sign here. You can make it clear? Clear, everyone?
Yes, sir.
Yeah, and the next 22nd to 0, that's what your mantissa. Okay, here they written as a fraction, but that's what we call as a mantissa. So the mantissa is used by 23 bits and the 8 bit is used by exponent, and 1 bit is used by sign. By here itself you can tell, I'm not going to tell you, you can do it on your own. You will see what is the maximum and the minimum number you can represent by a single precision. Okay, so do it on your own. Okay, so you can, this 8 bits is including bias. I'm leaving it for you as a homework. You have to find out, and you can later on tell me what is the minimum and the maximum number you can store in a single precision representation. Now coming down here, next line, that is your double precision. Okay, so how many bits you have total? Tell me. 64 bits. And now you see, of course, sine will take only 1 bit. Now you can add 11 bits for the exponent and 52 bits for the mantissa. So you can see this, of course, double precision can handle much larger numbers than a single precision. Okay. On the other hand, what happened? Your double precision is going to occupy more and more memory space. Am I right? Not just a memory space, when you do an operations also, all these bits has to be taken into account. So this can be more slower than your single precision. Okay?
Sir, in the sine bit,
Yeah.
is 0 for minus and 1 for positive.
Yeah, that is typically, I'm also not very sure about it. Mostly if it's 0 for minus and 1 for, sorry, it's the other way I think. So 1 for minus and 0 for positive. It's either of the one. Okay, you can just find it out. That's not a very, basically what I mean, you have to represent minus and plus, that's it. That's not important for us. We are able to represent minus and plus, that's it. Am I clear?
Yes, sir.
Okay, fine. So this is the way. So now, okay, this is the way a single precision and double precision is being stored. And now I'm, okay, so now I'm still my my claim of telling this computer is stupid is not justified, because you can see very well I have given, if I go for the double precision, I have given 11 bits for the exponent and the 52 bits for the mantissa. It is quite accurate. I am not going to, none of my physical quantity which I am going to deal have this much of precision. Okay, hardly we have 3 or 4 precision except the velocity of light. Okay, so I know all my physical constants which I am going to use, they don't have that precision that mantissa needs so much of bits. Am I right? And I can in fact represent all the numbers exact given this much of this many numbers of exponent and this many number of bits for the mantissa. Correct? So why I still call this computer stupid is because it is not, my computer is not there to just store the numbers and doze off. It has to do some operations. Am I right? I have to do some jugglery with the numbers. And that's where the whole mess this computer does. And how it is, let us see. How I will see how a computer, to see how a computer adds. Then you will understand how dangerous thing are you dealing with this machine. Okay, so for example, let us say, for example, let us, how a computer will add 2 floating point numbers. Okay, how it's going to add 2 floating point numbers is, for example, let me add up a number 0.00001 plus 10582.0. Okay, I want to make the computer to add these 2 numbers. How a computer adds is, I am going to show it in the decimal representation because that's easier for us to understand. Okay, I am not going into the 2 base system. So first what takes is, this takes this number, right? So 10528.0, this will be represented as 0.10528 plus is there into 10 to the power of, tell me how much is this? 5. Am I right? This is the way the computer stores. Plus 5. I am writing plus 5 because computer will handle the bias. And this number, what will be? 0.00001. This will be represented as plus 0.1 or whatever, 000 whatever into 10 to the power of minus how much? 4. Am I right? Am I making it clear?
Yes.
Am I making it clear? Yeah.
Yes, sir.
4. Okay. Actually, if you ask this computer to add, the computer cannot add to these numbers. How a computer adds is, the computer makes the exponent same, equal. Okay. So how it going to make the exponent equal is, so what it does is, so this is going to make it as 0.10528 into 10 to the power of 5 plus here, and this number also I have to write it as 10 to the power of plus 5. Tell me what will be this number here? Can you tell me? How many zeros?
9 zeros, then 1.
Correct. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros and 1. Am I right? Clear? And this is what stored as a mantissa, and this is what stored as a mantissa, and the computer had these two. You understood what it is doing? So it adds so many zeros, eventually this number, if there are some number instead of 1, I have 5, 6, 4, if it goes out of the mantissa, those numbers are lost. Correct? Respond?
Yes.
Can you understood the problem? So this is the way the computer adds. The computer makes the exponent equal and then adds. In making the exponent, see, either you take it as a become -4, again this becomes larger. Correct? 10580000. Whatever you do, it's going to become, your mantissa is going to become larger, and mantissa means when you try to make the exponents equal, some of the digits, some of the significant digits will eventually push out of the mantissa. You got it? And then the computer adds up. So those numbers, those information which are pushed out of the mantissa, we lost it. And that's what your all real and these operations will be, real number operations will be erroneous. Okay, or another way I can say, the computer will never able to understand while adding some two numbers, was there any significant digit beyond that, because by the time it makes the exponent equal, it has lost some of the digits. When you do all your do loop operations and adding many numbers, you have no idea in between making the exponents equal, the computer has swallowed some of your number. Okay, it has just throws the significant digits to the bin. Okay, so you will have that error in your computation. Clear now?
Then the size of the variable while
Pardon?
why can't it convert real into double integer?
Yeah, even double also same, na? See, the point is, suppose you are adding 10 to the power of 45.
There is no dynamically
Pardon?
plotted size for variables. Dynamic size for variables is not there.
No, whatever, if I ask you to add, this is the only way it can add. If you actually carefully look into it, there's no other way I can add these two numbers. It has to make the exponent equal. There's no other way you can add these two numbers. It's really a challenge. If you're able to overcome it, the computer becomes smarter. Okay. So, only way to add is you make the exponent equal, then only I can just add up both the mantissas. Okay. Otherwise, we just add the mantissa. That's it. Am I making it clear?
Yes.
Yes, sir.
Okay, so this is what your problem with the computer addition is. So this is something very important. That's what you should always remember. Every real operation, real number arithmetic operation in a computer is bound to have some error, because you never know, in the operation some of the significant digits may have been missed. That's what why in a Fortran you write an integer separately and a real number, declare an integer as an integer and a real number as a real, right? You could have asked why I need a integer at all. An integer also can be represented in the real notation. Am I right? Now you understand why it is important. Anywhere when you are writing the program, if your program is going to deal with the integers, stick to integers. Don't unnecessarily convert it into real number and add up these errors. Okay, these are the cautions. If you have your operations needs only integer operation, stick to integer operation. By converting into real, you are actually adding up the error there. Okay, so this is what very important when you are writing the program. Okay, so the best thing is, if your operations are handled with the integer itself, it is accurate enough. The moment if you are going for real numbers, you are bound to have these errors will be there. So so then we can introduce a terminology what we call as a machine accuracy.
Sir, what
Hi.
which exponent will it decide to convert to? There are two now, +5 and -4.
Yeah, exactly.
So how will it decide to convert which number to other exponent?
Oh, that I am not going into it. How the way the algorithm handles it, that we don't have to. I don't know which is made. Whether your question is whether this made is -4 or this made as +5. Am I right? That's what your question is.
Yes, sir. That's the question.
Yeah, correct. Means I am not sure about it. Okay, that depended by the how the architecture of the computer, what is the compiler you are using and all. They must possibly decide that. For us, what is important is it makes the exponent same. Either the same thing you make it as -5, still you are going to face the same thing. Am I right? All the thing will add up 0, 0, 0, 0, 0 here. Correct?
Yes, sir.
Yeah, so it's one and the same for us. The point is, the moment you are going to make up the exponent equal, we will lose some of the significant digits. Clear? Clear?
Yes, sir.
Yeah, fine. So then we are going to have a term, something called as a machine accuracy, epsilon n, or whatever is simple, doesn't matter. Okay, what the machine accuracy is? So machine accuracy is the smallest number which when you add with 1 will give you an answer which is not equal to 1. You got it? You can do this small program. What happened? You take 1 and keep adding a small number with the 1. It's okay. It's a very crude way you can do it out. Crude way you can find out that how this machine accuracy is typically like by just keep adding a smallest number which added with 1 will give you an answer different from 1. That decides your accuracy, how small the number can be. What is the typical machine accuracy? Clear, everyone?
Yes.
Okay, so this decides your machine accuracy. So machine accuracy is the smallest number added with 1 will give you an answer which is not equal to 1. That means at least the presence of the number is there in that 1. So that decides your machine accuracy. And anything, if you have anything smaller than that, you are lost. Any number smaller than epsilon m, the computer will not see it at all. But remember, it appears this epsilon m is a very small number. That is not always true. Okay, so before I'll come, so every arithmetic operation, whatever the arithmetic operation you are doing, you can blindly say every arithmetic operation is going to have an error at least the order of this one. Correct? Rake up the pen.
Yes, sir.
Yeah.
Yes, sir.
So all arithmetic operation is going to have an error at least the order of epsilon m. Okay. And now remember, in most of the cases when you go into integrations and all, you do some 200 times the loops. There can be double integration, triple integration. So all this nested integration goes to the power. Okay, so if you have every loop has 100, so 100 to the power of 3. So you make 1 million operations or 10,000 operations. Okay, so 10,000 operations is going to each operation, that's inside the loop. Inside you will have a lot many additions. Am I right? All the addition is going to, each addition is going to have your epsilon m keep adding. Okay, and eventually this can go, means this can become so high, it can give you wrong answers. What they say is, but the epsilon m can be positive as well as negative. Okay, if it is normal, so then you can say, suppose if you have a n operations, okay, and if your these errors are actually equally having the if the errors are randomly distributed, okay, so then you can have a positive epsilon m and negative epsilon m for n operations. You will typically, the error you will get, it will be n time root of n times epsilon m. Am I right? This is what you will get for the, if the errors are randomly positive and negative randomly means random signs there, randomly does there, then this is what you will get the maximum error. But this is what I say, if you get this root of n times epsilon m, this you are lucky. Most of the times your algorithm will have a form, the machine accuracy will be unidirectional. It will be either always positive or negative. So you will get n times of epsilon m, not the root n times of epsilon m. Most of the cases, this is what happens. This will, if you are extremely lucky, you will get it, but most of this won't happen. So you will add up the error for n operations, you will add n times epsilon m. You think this is what the error you are going to get in your computation. This is your best case situation. Okay, and not just.
Once again, how did we get a root n epsilon?
Yeah, this is randomly distributed. Suppose, see, what I am saying is your epsilon m can have two, it can be positive as well as negative. Am I right? Machine accuracy. The error can have positive as well as negative. And suppose if you are doing n arithmetic operations, and if the n operations, if the errors are random, it can be positive, negative. So then it can, means what is the, because at one case it is added, error is added, another case error is subtracted. So there can be reduction also. The net error will be typically root of n times of epsilon m. Correct? You got it? So now on the other hand, if your errors, though the error can be positive, negative, sometimes most of the case, I can't call sometimes, most of the cases, the algorithm we make, it will make it unidirectional. It will be either plus epsilon m or minus epsilon m. So, and when you do that, for n times, you are going to add n times epsilon m. Am I making it clear now? Clear?
Yes, sir.
So this is what happens when you are dealing with the machine accuracy. Yeah, there's something I remember. But the one thing I have to mention is, don't think machine accuracy, this is the error. This is the typically the smallest error you can assume you introduce by adding this operation. The error means your error can be much larger than that. For example, if you are subtracting two large numbers. So for example, let us say I am going to subtract 10 to the power of 45 minus 10 to the power of 20. You got it? So the moment 10 to the power of some numbers are there in front, yeah, I should have written that. 3.26 into 10 to the power of 45 minus 5.28 into 10 to the power of 20. Okay, suppose for example I am subtracting these two numbers. Now this number exponent has to made as 40, correct? Am I right? Is that make correct? Either this one or this one may brought to 20. So then what happened? This number, how many zeros you will add up? Think of. Correct? 0.00000, you have to add some 10 to, means, correct? In that case, you eventually push this 5 to 8 so far away from the mantissa, your error will be the order of 10 to the power of 20 or 10 or 9. Am I making it clear?
Yes, sir.
Is that clear? So this is what? The moment when the numbers are, when you are handling with the large numbers, you have pushed your significant digits so far away from the mantissa. And so that's why you are going to add up the machine accuracy what are the machine accuracy? This is not the error you will get. Your errors can be much larger than your epsilon m. So this is a second important caution you should remember when you are handling your problems in a computers. Never use large numbers. Okay, if your problem is involving large numbers, scale it down. Nilay has already told you also, right? You have to either you scale it down or represent your whole problem in a logarithmic scale, so that will save some of your life. Okay, you got it? So these are the cautions we should have while adding this real numbers in a computer. So this is what, and so every operation is going to, every arithmetic operation in a computer is going to have an error because of the machine accuracy. And that error, you call it as the round-off error. Got it? So this is what we call as round-off error.
So,
Yeah.
Even if we scale down our numbers, let's say we have a program where we have to do some thing for long loops, let's say 5 million times.
Yeah.
The errors keep adding up, right?
Yes, yes.
How do we counter that?
How do we counter?
Yeah, so how do we minimize the error from that?
Correct, correct, correct. A very good question. That's precisely your numerical technique is. You got it. That's precisely what we deal in a numerical technique. The whole rest of the course, you will eventually see how we are going to reduce by, see, you can't avoid adding. Of course, you have to add, right? All we can do is, we will add it minimum number of times, right? Am I right?
So we choose the appropriate method.
Algorithm, precisely. How algorithm you are going to choose, this is all decided by this round-off error. Will come one more error. So, and these two errors is what which it says certain algorithms are better than certain algorithms. When I give it 2-3 algorithms, suppose for example, you must have done about it. In your integration, you are doing Simpson's 1/3 or trapezoidal or something. I want to ask you, what do you compare with the algorithms? Okay, normally you can put up the case, okay, one is linear, another one is goes up to second order, third order or something. I can always say by increasing the number of grids, I can approach both of them to be similar accuracy. Okay, so what decides which algorithm is better than what? Okay, that is this quantity. So this is what we call as a round-off error, and this round-off error is introduced by your computer. That's why I wrote in that flow chart, that box diagram, I put the computation is give you the error, there's a round-off error. Okay, so now this is a one part of the error. So numerical method techniques is not just dealing with this. There's a one more error, important error comes up, which we will see it in all the upcoming lectures, but I will give a small introduction of it. So you have done one example also. Nilay has given an example, correct? So Nilay has done something. While I was editing his video, I remembered he got some function called as myCos. Am I right? You remember that? He basically developed, he didn't like the cos function used with a Fortran program. He wrote his own cos function, correct? By using the...
I am unable to see your board.
Okay, perfect. Yeah. So this is... yeah. So now... this is what the round-off error we saw. Now there is another important error which is not by the computer, which is introduced by the algorithm. That error you call as a truncation error. Okay, in a simple language, if I want to say what do you mean by this truncation error is, it is our inability to handle infinity or infinitesimal. Okay, that gives rise to an error which is called as a truncation error. For example, if you, let us take for example, you have done it, Nilay has done in the program. Suppose if you want to find a cos of a function, if you want to write a program to find a cos of a function, what do you use? You use the series expansion for the cos function, and then you find out the cos of the function, right? But now cos series is an infinite series. Am I right or wrong? Correct? Correct?
Yes.
So now I can't keep adding it for infinity, right? So at some point I got enough, stop it. So that means I can't deal the infinity. I have to make it finite at some point. So that means all the rest of the numbers, whatever I left, they are basically errors. That's what you call as a truncation errors. Similarly, in case of an integration, what do you do?
Can't we go till like we only lose after the how much real number can store, so that we can minimize it?
We will come there. We will come there. At some point we have to. I will come there. That's not even. There's much more worse thing is going to happen there. I will come there. Okay. So the second thing is another possibility. Other cases is integration. Integration of f of x dx. Correct. A to b. The moment what you do numerically, you will see all this integration is eventually converted into summation I equal to 1 to n. Am I right? So your dx is an infinitesimal, and what you do here is f of x into delta of x, correct? Delta of x will have a finite width depend upon how much divisions I have made. We will see this in when you deal the integration part. Okay, so again, here is, I can't represent an infinitesimal. You can see as I make it smaller and smaller, delta x means when I make n larger and larger, this will approach closer to my integration. Correct? So, but I can't make it as small as dx. At some point I have to stop it. We will come to where we will stop it, I will come to there. So that beyond that I can't go. So that's also gives rise to an error. So these types of errors you call as your truncation error. Now, why I have to stop? Why I can't go beyond delta x, or even the question what he asked in the cost function, I have a series which is an infinite series, some value I have to stop. Why I have to stop at some value? What is going to decide? Because you see, if I want to have a more accurate represent of the cost value, I have to keep adding more and more and more and more element, more and more terms, right? Each addition is going to introduce your round-off error. As I keep adding more and more, I am going to build up the round-off error. You got it? So to reduce the truncation error, I keep increasing my terms as long as possible. I keep adding the terms more and more. But that is going to cost me in terms of a round-off error. You got it? So same way here also. Am I clear?
Sir, how is it contributing to round-off error?
Correct. What is the round-off error? Any two arithmetic operations will have an error, which is at least the order of machine accuracy. It can be even larger than that. Am I right?
Yes, sir.
That's what the error is. Suppose if I want to find a cos, for exact representation of cos, how I am going to calculate the cost function? I am going to go for the series solution. Correct? And this is an infinite series. Okay. If I add infinite terms, think of what will be the condition of the round-off error. I am adding more and more terms.
After a certain point, it won't matter because our storage is finite, so it will truncate.
No. Correct, you are right. But this, okay, we will do an example. Today I will give you one exercise. That's the one example to show how this round-off error can actually make a havoc. Okay, so yeah, this is not that beyond the storage or something, because see, the moment, that's what I'm saying, the moment you keep every additions will have this error, okay, and after a certain point, means your round-off error, because as you see, it goes like this. So when I keep adding, so suppose if I call this is a truncation error and this is a round-off error, okay, so I will call this truncation error, this is a round-off error I am going to do, and as I keep adding terms more and more, any expression, okay, the truncation error goes down, right? On the other hand, your round-off error, when you add the first term, round-off error will be minimal, only one number, right? As you keep adding more and more term, the round-off error will keep increasing. Okay, and this is not just decided by your the amount of memory location what you are giving for your real number or means your mantis or exponent. Of course, it can go beyond mantis. That's what the error is going. Your whole round-off error is coming up. You understood the point? We are actually adding up more and more smaller terms to it. So now that terms, you will see eventually what happens. Those terms, you may assume that will eventually modify your the least term only. But as you keep adding more and more, and when you do operations more and more, those errors can come into can create a problem with you. Okay, we will take one example with that you will be able to understand it clearly. Okay, so what I want to tell you here is, the way if I wanted to reduce my truncation error, what I face is my round-off error will increase, because reduction of a truncation error needs more and more additions or more and more operations, but more and more operations is going to increase your round-off error. So you have to basically get a trade-off between the truncation and round-off error. And the whole, that's why again, when I come back to the numerical method and numerical techniques, the whole thing is to how you can reduce this truncation error without increasing arbitrarily this round-off error. Having both of them in a proper handle and dealing the problem, and that's what in a more broader sense we can call that also a whole numerical technique. Am I making it clear?
Yes, sir.
Okay, so and I guess we are already crossed the time. Okay, so in fact I thought I will be able to show the demo. Anyway, so what we will do is, so with this I will stop. So you understood what is the errors in these numerical methods. So tomorrow we will start up, I will put up an, I know you all must be knowing for programming very well. I will give you a problem now. In a short while I will send you, and I want you to write the program and keep it ready for tomorrow. Okay, so in the tomorrow's class we will start with a demo. We will try to see how we will take a very simple problem, a very simple and very efficient problem algorithm, and we will pick up that and we will see how miserably that fails because of the roundoff error. That is one of the because I found that's a very interesting problem which can give you a warning how dangerous your calculations can be when you are dealing with the computers. Okay, so and with that I will stop today's lecture. Okay, we will see tomorrow and start with the demo. Okay.
Sir, I have a question.
Yeah.
When we are deciding multi-sign exponent size of that,
Okay.
is it decided by the processor or can we allocate it according to our use?
No, that because these are all actually, there must be a way, I am not very sure, but there must be a way to manipulate those things. That's a very high level programming you have to come. Most of the cases what happens, all the programs you will do when you write in a Fortran program, when you put real star 8 or real star 4, am I right? Just real. So it simply allocates, that's the way the compiler has decided, that the way the memory will be allocated. Okay, now if you wanted to modify that, basically that what you are asking is you are going to one level beyond the Fortran compiler.
Yes, sir.
I am not sure whether you will be able to do it within the Fortran Fortran compiler, or maybe you have to go much deeper into it.
Okay, sir.
You got it? Yeah. But most of the cases, I will tell you, most of the cases you can see today's, whatever I am telling you today, this may not be very, it may look very silly in case of, in today's scenario, because you are having a high speed computers. See earlier what happened, why the people use a single precision? Why the people preferred integer? Why the people in single precision, not double precision, is because of the speed. Older computers were slow. The moment I use double precision for my all the variables, okay, the computer keep dragging. Okay, so then to make the process fast, I start using the single precision. Okay, now to extent we have quite a fast computers, we can actually work on double precision itself, but still I would say I can show you some of the problems where by using double precision will take you enormous amount of time to calculate. Okay, so you may have to get back into single precision to get your job done. Okay, that's more of a statistical fitting and all when you do. Okay, of very complicated functions or something when you do, your double precision can cost quite amount of time. Okay, so that's what the whole idea is. It's better to have this idea, knowledge, that what are the numbers I am supposed to handle. If your study says you are safely handled with a single precision itself, because your numbers are not very large numbers. Your whole process is going to deal with a very small, small magnitude numbers. Then you go with a single precision. Don't unnecessarily stick to the double precision. That is like the best thing is to use integers. Of course, if you are able to. If you can't, come back to real numbers, floating point numbers. But with a cautiously, you have to work on it. Clear?